Iniciamos con la conferencia magistral. This is the time to start with our plenary speaker, Professor Virendra Mahajan, who will give us the conference called Axial Irradiance of a Focus Beam. Applause for him, please. First, I'm going to make a brief introduction about Professor Virendra Mahajan. Dr. Virendra Mahajan is a graduate of the James C. Wyatt College of Optical Sciences, University of Arizona, where he is an adjunct professor. He is also an adjunct professor at the College of Optics and Photonics in the National Central University in Taiwan. He has Please be quiet. He has 40 years of experience working on space-based civilian systems, the last 31 with the Aerospace Corporation, where he retired as a distinguished scientist. Dr. Mahajan is a fellow of SPI-OSA and the Optical Society of India, and recipient of SPI's 2006 Kennedy Award and 2015 Educator Award. He is the author of 5 books on optical imaging and aberrations, all published by the SPI Press. He is also an associate editor of OSA Handbook of Optics 3rd edition. Thank you very much.
Good morning to you all. The theme of the conference is Axial Irradiance of a Focus Beam. The demand of high optical resolution has brought researchers to explore the use of beam shaping diffractive optical elements for improving performance of high numerical aperture optical systems. Diffractive optical elements can be designed to modulate the amplitude, phase, and/or polarization of a laser beam such that it focuses into a targeted irradiance distribution or point spread function. The focus point spread function can be reshaped in both the transverse focal plane and along the optical axis. Optical lithography, microscopy, and direct laser grading are but a few of the many applications in which a properly designed diffractive optical elements can significantly improve optical performance of the system. Our guest, he's a graduate of the College of Optical Science in the University of Arizona, where he is an adjunct professor. He was a distinguished engineer at the Aerospace Corporation in El Segundo, California, until his retirement in May 2014. He has taught short courses on optical aberrations at the annual meetings of the Optical Society of America and SPI. He has published numerous papers on diffraction, aberration, adaptive optics, and acousto-optics. He is a fellow of the Optical Society of America, SPI, and the Optical Society of India. He was a topical editor of optic letters in the area of optical imaging diffraction from 2002 to 2005. He is the author of Aberration Theory Made Simple in 1991 editor of Effects of Operation in Optical Imaging, 1993, author of Optical Imaging and Aberrations, Part 1, Ray Geometrical Optics, 1998, Part 2, Wave Diffraction Optics in 2001, Part 3, Wavefront Analysis, 2013, and Fundamentals of Optometrical Optics, 2014. He has the Educator Award in 2015 from SPIEC, Applied Optics Laboratory named after Dr. Mahayan in 2008, and the A&E Conrolli Award in 2006, also from SPIEC. Please welcome to Dr. Brenda Mahayan.
Hello. Buenos dias. Thanks to Professor Alfonso Padilla, Professor Karina Trotsky, and many others. First thing I want to tell you is I love Mexico. And I love Mexican food. But I am vegetarian, so I know only about the vegetarian part of Mexico. My wife, who is here, her name is Shashi, she is not vegetarian. So she knows the rest of the Mexican food. And it's a beautiful day. I have been to many places in Mexico. Torrenzintla, Puebla, Leon, Monterrey, where I have given courses, where I have given talks, but I think I love Tulancingo more than any other place. It's a small city surrounded by hills. And you may not know, but I have a casa, room number 28 at the Hotel English. I stayed there a year ago, I'm staying there again now. And if I'm invited again, I'm sure I'll be staying in that room. Thanks very much for inviting me. I'm impressed that there are so many people. When I was first asked if I would give the talk, I thought I'll be talking to the optics students only. Some that I know from the past, and some that I came to know this time. But then I realized, I'll be talking in an auditorium. Can you hear me okay in the back?
Yes. Yeah.
Very good. I have been here already for more than 2 weeks, and my wife and I will go back to Los Angeles on Friday. Los Angeles has been our home for the past 35 years, even though I was a professor in Tucson, where I studied myself in the early 70s. And I have taught there for about 8 years. I used to fly from Los Angeles to Tucson, give a 3-hour talk, and come home at night. It used to be 14 hours a day, sometimes 16 hours a day, and so on. But that is what I did when I was a little bit younger. Not too much younger, but a little bit younger. I'm going to talk about the axial irradiance of a focused beam. I chose this topic because there are some surprises which I hope you will find and appreciate. What this is about is, if you focus a beam, consider a laser beam or a uniform beam. Thank you. I know I need water when I'm talking in my class for 3 hours. And since I'm the one talking and talking for 3 hours, you get thirsty. And of course, last some days it has been nice and warm, which I love. So anyway, if you focus a beam and you make the observation along the axis of the beam, what would you find depending on the conditions of the beam? That's what I'm going to discuss. It is natural to expect that when you focus a beam, the maximum irradiance power per unit area, the maximum brightness of the beam should be at the focal point, where the beam is focused at. However, it depends on the parameters of the beam that it may or may not be the brightest point. Why it may not be the brightest point. Second, if we have a perfect beam, and that means no aberration in the beam, aberration-free beam, is it possible, whereas in general you introduce aberrations, the value of the irradiance at the center goes down because of the aberration. But I'm going to show that depending on the parameters of the beam, it is possible that the irradiance of the beam at the center may go up instead of going down. And I hope as I go through my charts that you will get some idea about and appreciate why it is that it could go up, even though we will introduce aberration in the beam. Here is Daniel. So these are the topics I'm going to talk about. Point spread function. In optics, the image of a point object we call the point spread function, meaning the light spreads, although based on geometrical optics, you would think it's a point, but actually it's a distribution we call the Airy pattern. And I will mention what that is. Those who are from electrical engineering, what we call the Airy pattern, they call the antenna pattern. But the physics is the same for both. Of course, the wavelengths, optical wavelengths are very short, and microwave wavelengths are very long. I will talk about Strel ratio. Strel ratio, named after the name Strel, called Strel, that the ratio of the central value in the presence of aberration divided by the corresponding value when there is no aberration. And that value is always less than or equal to 1. Cannot be more than 1. I'm going to talk about defocus aberration. Very good. It's not good to point at people. Defocus aberration. I'm all about aberrations. If I don't talk about aberrations, I don't know what to talk about. I will write defocus aberration in terms of this Fresnel number. I hope some of you know from your physics what a Fresnel number is. And I will, of course, tell you what it is as we get there. Then I will talk about axial irradiance for small Fresnel numbers and large Fresnel numbers. And I will, at some point in time, give you the example of a system with a small Fresnel number and a system with a large Fresnel number. Axial irradiance larger than the focal point value. I will demonstrate that. Demonstrate only on paper on the screen. And then increase in axial irradiance due to some aberration. And I'll give a couple of examples. Whatever I'm going to talk about, much of that is contained in this book, which was second edition, came out in 2013. I'm afraid to point there. because there are people in between. So anyway, irradiance distribution of the image of a point object. Let's assume we have a perfect system, aberration-free. We have a point object, and we look at its image. The image light distribution is given by this formula. P is the pupil function. It represents the complex amplitude at the pupil. Lambda is the wavelength of light. R is the distance at which the image is being formed, so to say. In the case of a beam, it will be the focal distance. The integration is done over the pupil. If it's a circular beam, it's integration over a circular region. And this integral is the Fourier transform of the pupil function. And we take the modulus square because we are interested in the irradiance, not the complex amplitude, but the irradiance, power per unit area. 1 over r square represents the inverse square law. And 1 over lambda square is how the dependence is on the wavelength other than the wavelength dependence here. And this is inverse square law on the wavelengths, you could say. Smaller the wavelength, smaller the focal spot, and therefore higher the brightness. The result of this integral was given by Airy in 1835. He was a royal astronomer, he worked in London, and 1835 was long ago. We still read what we call the Airy pattern. And this form of the Airy pattern, in terms of the first order Bessel function of the first kind, was given by Rayleigh in 1881. It took a long time between 35 and 81 to get to this form. If you look at Airy's original paper, you don't find this formula there. He has written it in terms of an integral, and it's amazing, he calculated that integral by hand in 1835. Even though these Bessel functions were known or given by Bessel 17 years before Airy wrote his paper, 17 years before. But in those days, maybe communications were obviously not as good as it is today. And maybe he was not aware that the integral he had was actually the first order Bessel function, and of course square. It's just a little bit of history in case. So anyway, Airy pattern in the form given by Rayleigh. The radial distance r in the plane of the image or the focal plane is in units of lambda f. F is the focal ratio. And I say focal ratio, I didn't say f number. Sometimes it is the f number. But there is a difference between the two, and optics students, I hope, know the difference. So let's look at that Airy pattern. The Airy pattern, it is the image of a point object. Based on geometrical optics, you expect a point. But based on diffraction, you find there is a central bright spot surrounded by alternating dark and bright rings. The contrast, because of the light, etc., is not good, but there are many dark and bright rings which are getting weaker and weaker in brightness. The central bright spot has a radius of 1.22 in units of lambda f, called the Airy disk, and contains most of the light, almost 84%. The diffraction rings, so-called, contain the balance of it, about 16%. The central point is the brightest. We think in terms of, well, it's the focal point, it has to be the brightest. And that's okay. However, there is a better explanation. That explanation is that the Huygens secondary wavelets, they are all in phase at that point. And therefore, they interfere constructively and give the maximum brightness. If there are aberrations, then something else happens. Those Huygens secondary wavelets are no longer in phase, and therefore they do not interfere constructively. Therefore, the value goes down. And this is something I would like you to keep in mind as we make progress. I think there is a time delay. Curve ratio. I said because of the aberration, the value at the center goes down. How much does it go down? Can we estimate? Curve ratio represents the ratio of the aberrated central radius and the aberration-free central radius. So it is I of 0 with aberration, without aberration. And phi here is the phase aberration, W is the wave aberration. And two are related by the factor of 2 pi over lambda. For small aberration, curve ratio is given by e to the minus sigma square. If sigma square is large, curve ratio is small. If sigma square is very, very small, curve ratio is still close to 1. Where the phase aberration variance is given by this expression. And I wrote this paper in '83 when I was a young man. '83 was long ago. Beam focusing. Here is a beam shown at the exit pupil of the system. It's focused at the Gaussian image plane, in the focal plane. And if we make an observation along the axis, we are making observations in the presence of defocus aberration. And we will see how that impacts the axial irradiance. Beam is focused at a distance r. We are making an observation in a distance z. So slightly out of focus, maybe quite a bit out of focus, depending on the Fresnel number. And let's talk about the Fresnel number. First of all, defocus aberration. If the beam is focused at a distance r, observation is made at a distance z. The defocus aberration is given by this expression, and I can write it in terms of this, where maximum value of r is the radius a of the beam at the pupil plane. And so I can write the peak defocus phase aberration multiplying by 2 pi over lambda in this form. And we will now talk that a square over lambda r is the Fresnel number n. What is a Fresnel number? Here is the pupil plane, radius a, focal point at a distance r. Fresnel number represents the number of Fresnel's halfway zones. The pupil, how many halfway zones does it have? How do we calculate? This distance is r, this distance is r plus n times lambda over 2. N is the Fresnel number, lambda over 2 represents a halfway zone. And this is the diagonal of this right angle triangle. Square it, expand it, and lambda being a very small number, we neglect the lambda square term, and eventually we find n equal to a square over lambda r. and gives the number of Fresnel's half-range zones. This expression, a square over lambda r, I wrote as n, the Fresnel number. And looking at this expression, you can see that if n is very large, z and r cannot be too different from each other, because otherwise the defocus aberration will be too much. If n is very small, then they can be different from each other and still not have a very large defocus aberration. Large Fresnel number, small depth of focus. And that's the example of a photographic camera. And I'll give a numerical example in a minute. Small Fresnel number, large depth of focus. That's the example of a laser transmitter. And we'll consider that example. Defocused PSF. Now I have replaced that pupil function P by this. E to the I B sub D rho square, where B sub D is the defocus phase aberration. And J0 is the zeroth order Bessel function. If I let B sub D equal to 0, we get back the 80 pattern. Defocused PSF for large Fresnel numbers. This is the 80 pattern, half a wave of defocus, one wave, 1.5, 2, and 3. One thing you notice is if it is an integral number of waves, B sub D equal to 1, 2, 3, the center is dark. Center is dark because for integral number of waves, the central value goes down to 0, or Stroll ratio is 0. By the way, if you have any question, feel free to ask any time. Just yell, I have a question. And that's okay. Now, if n is small, we have to redefine Stroll ratio. Stroll ratio represents the effect of aberration on the central value. However, the central value depends on r as 1 over r square. So when it is z, it is 1 over z square. If z is less than r over z is greater than 1. And r over z when squared is even larger than 1. Therefore, it can have impact. So, we define the Stroll ratio, axial irradiance at a distance v, beam focused at a distance r, divided by axial irradiance at the same distance z, beam focused at a distance z. So, in one case, the beam is focused at a distance r, in the other case, it is focused at a distance z. The observation is made in both cases at a distance z. So this is a common factor as far as the inverse square law dependence is concerned. The only impact that occurs in the definition of the Stroll ratio is the aberration, the defocus aberration. Okay, if you carry out that integration, then you can carry out the integration in the closed form. This is the result. It is in units of the focal point value. This number, sin x over x squared, is less than or equal to 1. It represents the Stroll ratio. Stroll ratio has to be less than or equal to 1. We said aberrations will reduce the central value. R over z squared represents the inverse square law dependence. And you notice this number is less than or equal to 1, this number can be larger than 1 if Z is less than R. Z less than R means the beam gets focused at a certain distance, we make the observation closer to the pupil. Z less than R. So, there are two competing factors, increase due to inverse square law dependence for Z less than R. And this is significant only for large depth of focus. And we get large depth of focus when n is small. Second factor, decrease due to defocus aberration, non-constructive interference of Huygens secondary wavelengths. Meaning, defocus aberration reduces the irradiance regardless of the value of n. Aberration will only reduce. So, axial irradiance closer to the pupil can be higher than the focal point irradiance if the increase due to inverse square law is larger than the decrease due to the defocus aberration. I hope that is clear. Next, I show some results. For different values of n, the Fresnel number 1, 10, 100, I show the axial irradiance. One more time, axial irradiance meaning you have a beam that is focused and along the axis you walk with a detector and keep measuring the irradiance on the axis. When n is very large, and 100 is not very large, but it's large enough, this is the axial irradiance. And it is symmetric about Z equal to R, meaning symmetric about the focal point. But notice, it is very narrow. As soon as you go away from Z equal to R, it goes down quickly and reduces to very small values. For n equal to large, n equal to 10, something similar, but now the beam has kind of, the curve has extended. And notice, it is asymmetric. Asymmetric because of the inverse square law effect. If n equals 1, see how asymmetric it is. The focal point is here. Focal point value is unity. But look how much larger the irradiance is along the axis for smaller values of Z. How much larger? Almost twice as much. 1.9 times. Almost 2. Focal point value of unity. But over a large range, the value is higher than 1. Simply because of the inverse square law effect. Inverse square law effect this is better. Thank you very much. Which is better? She says you're welcome. I wish I knew Spanish, but I know a little bit about physics and optics, but Spanish only a few words. But when our two kids are young, high school, we made sure they learned Spanish. They took Spanish for 4 years each. And my daughter, she can talk to you in Spanish. Maybe not as good as you, but she can hold a conversation. Our son can also understand and talk some Spanish, but not as much as good as daughter is. Our son is a professor at Stanford. He's an ophthalmologist, and he doesn't get the opportunity to talk to people who speaks Spanish only. So he doesn't get time to opportunity to practice. But anyway, thanks very much for this microphone. Okay, just very quickly, at the peak value, which is about 0.6, 60% of the focal range, or n equal to 1, the wave aberration, defocused wave aberration is only number 3, third of the wave. But the Strong ratio is 0.68, the inverse square law dependence is 2.78. You take their product, 0.68 times 2.78, you get 1.9, almost 2. Okay? So far so good. Now, think of the following question. For small Fresnel number, the irradiance at a shorter distance, shorter than the focal point distance, the value is much higher. Now we ask the question, suppose I have a laser beam and I have a target that I want to illuminate. Target is at a certain distance z, and I have a laser beam whose focus I can shift. I have a control that I can shift its focus. And since I worked for the Air Force, for the military, I use the example, there is an enemy tank that I want to burn, that I want to disable. So I'm going to focus a beam on the tank. Where should I focus? I have this control. I can focus it wherever I choose to. Should I focus on the tank? Beyond the tank? Or closer than the tank? I would like you to think for a moment, where should I focus the beam? Should I focus the beam on the tank? A little bit further than the tank? Or a little bit closer than the tank? You understand tank? Everybody understands tank? So what's the answer? Most of the time I get the answer from the audience. Oh, focus it beyond so that on the tank the value will be higher, which is true. Will it be the highest value possible? The answer is no. Why? The distance of the target is fixed. Therefore, inverse square law dependence is fixed. 1 over z square dependence is fixed because the target is at the distance z. And if I focus it anywhere else other than the target, there will be defocus aberration. And defocus aberration can only reduce the value. And therefore, I must focus the beam on the target, not somewhere else. Does that make sense? You can say yes or no. Think about it. Let me illustrate. Now, z is fixed, r is a variable. And so, my parameter is now r over z. Z is fixed, r I can change. Again, n equal to 1, and z equal to 10, and z equal to 100. This is n sub z, meaning the number of Fresnel half-wave zones for the distance z. And you notice in each case, r over z equal to 1. That's where the mean is. R over z equal to 1. R over z equal to 1. By the way, the solid terms in each case,
previous ones, is for the uniform beam. If you have, in fact, a laser beam which has the core of a Gaussian, that is dash curve. I sub G, I sub Q. So far, so good. Let me continue. Maximum central irradiance on the target is obtained when the beam is focused on it. That means choose R equal to Z. Let's consider numerical examples. Photographic camera. The diameter of the lens is 2 centimeters. Radius 1 centimeter, small lens. Let's say the focal range, the distance at which the image is formed is 10 centimeters. Lambda, visible light, 0.5 micrometer. N equal to A square over lambda is 2000. That's a large Fresnel number. Stir ratio of 0.8 is obtained when V sub D is only quarter wave. The defocus aberration is only quarter wave, which corresponds to a longitudinal range of only 25 micrometers. That means the depth of focus is very small. And you know that from everyday experience, at least you used to, when the cameras were not out of focus. Nowadays, all cameras in your smartphones, they have automatic focus. You never get to experience to focus it. But if you have that opportunity, you will find as soon as you move a little, the picture becomes blurry. Meaning the depth of focus is very small. And here in this example, I'm saying the depth of focus is only 25 micrometers. Not even a millimeter. That means the effect of inverse square law, the 1 over z square, is negligible. Whether you are at 10 centimeters or 10 centimeters plus minus 25 micrometers, the value of z is the same. Very negligible difference. However, let's consider a laser transmitter. Here I'm going to make up the example so that the Fresnel number is 1 because we have numerical results for it. The beam is 25 centimeters. Distance is about 1.5 kilometers. The enemy tank, close range, still 1.5 kilometers. Wavelength 10.6 micrometers. That's the CO2 laser. Fresnel number n is unity. This is the other expression for the defocus phase aberration. And the stir ratio is 0.8 as long as the target, the distance z is between a kilometer and about 3 kilometers. Long depth of focus. Star ratio is still 80%. No matter what that z value, as long as it is between 1 and 3 kilometers. V sub d becomes significant only when z is much different from r. Principal maximum lies at 0.6 r, which is about 0.88 kilometers, with a value of 1.9 times the focus. Okay so far? I still have time, right? Now, I'm going to consider the axial irradiance of an aberrated beam. Keep in mind, this beam, which so far has been a perfect beam, perfect in this sense, at the pupil plane, the wavefront is exactly spherical, comes to a focus at the focal point. However, the thing to really keep in mind is that as we make observations along the axis, we are not observing only at the focal point, and therefore, except for the focal point, wherever we make an observation, there is a defocus aberration, even though the beam is perfect. But as observed from a point at a distance z other than r, the beam is not perfect, even though it has a spherical wavefront. Large Fresnel number, we already said the inverse square law dependency is negligible. Small Fresnel numbers, axial irradiance is larger at points closer to the focusing pupil, meaning z less than r. Now, these people, these two are Japanese scientists, these two are European scientists, they did their work and they found some result which I am going to discuss. And they were very surprised, very shocked. So much so, these people said propagation and focusing of a Gaussian laser beam beyond the conventional diffraction limit, going beyond the diffraction limit. We are not in reality going beyond diffraction limit. There is some other reason for the results they obtained. And the Europeans said, it's very unexpected result. At least they were a little bit wiser not to say beyond diffraction limit. But they are surprised. This is unexpected. We will show there is nothing that is unexpected. It is based on the effect of aberration in reality. Unexpected. Thank you. However, these results are neither beyond the diffraction limit nor unexpected. They are a case of balancing of defocus aberration with spherical aberration. There is defocus aberration when you make an observation at a point other than the focal point. Now you introduce spherical aberration. If the spherical aberration is of the right sign, positive or negative, depending on the sign of the defocus aberration, the two balance each other and reduce the effect of defocus by itself. And therefore, the value goes up. Here, I consider the defocus aberration. Where is the defocus aberration coming from? Because I am making an observation in a plane other than the focal plane. I add a certain aberration to it. What aberration do I add? Spherical aberration. Where is the spherical aberration? Carolina, as you know, wrote it before. And given a certain amount of rho square term, what is the value of A sub S such that the sigma value, the standard deviation of the aberration, is minimized. And that value is given by this expression. A sub S equal to roughly minus B sub D, but not quite, minus 15, 16. And similarly, if I consider the stigmatism, which is rho square cosine square, that value of A sub A is given by this expression. What happens to the sigma value? Defocus by itself, this is the sigma value, case of that. When balanced, the value goes down. How much? A factor of 4. If the sigma value has gone down by a factor of 4, the value is going to go up. The swirl ratio is going to increase because I have reduced the value of sigma. And similarly, in this case. Let's look at some results. Irradiance at a distance z, and it is the axial irradiance. Z as a function of z over r. The focal point is here. No spherical aberration. This is how the axial irradiance is. But for values of z less than r, if I choose this value of spherical aberration, minus 5 over 16 lambda, this is the axial irradiance. And you can see it's much higher. If as I change the value of defocus aberration, I continuously change the value of the spherical aberration that it minimizes the sigma value. This is what the axial irradiance is. So even though aberrations do reduce the value, but here we had the defocus aberration that was reducing the value. We were balancing it with spherical aberration, and we were reducing the sigma value by a factor of 4, and therefore the value kept going. Now, there is a minimum here, maximum again, but you can see these numbers are much larger than in the absence of spherical aberration. This is in the case of astigmatism. In the absence of astigmatism, this is the axial irradiance as I walk along the axis of the beam. I introduce astigmatism, the values are high. Does that make sense? Are you surprised? I hope so. Now, you may think that by choosing this Fresnel number so small, I am kind of tricking. This is only on paper results. It's only a mathematical result. But I want you to know that the minimum value of n, the Fresnel number, I chose the number 1, but minimum value is 0. A collimated beam, instead of a focused beam, a collimated beam is a real beam. Collimated beam means it is focused at infinity. And what is the Fresnel number in that case? N equals a squared over lambda r. If r is infinity, n is 0. So it's in fact real. And this is the, I guess you could get similar results for, let me see if I have it. So anyway, conclusions. You can have a large depth of focus if n is small. You can have, as in the case of a laser transmitter, and you can have a small depth of focus if the number is very large, as in the case of the photographic camera. Axial irradiance can be higher at distances z less than or equal to r. Aberrations can in fact increase the value because you are balancing the defocus aberration with the aberration you are adding. Now if I add some other aberration that does not balance it, does not reduce it, then what I do may not happen. But those are my conclusions, and I hope you find the talk interesting. If you have questions, please feel free to ask. If you don't want to ask now, you can write to me later, and that's fine. Thanks very much.
Thank you, Professor. PhD degree students, master degree students, any questions about the conference? No questions? Ana Rosa.
First of all, thanks for your conference, Professor Mahajan. And my question is, what's the definition of a phase aberration?
Very good. If you know the definition of wave aberration, which means the deviation of the actual wavefront from a spherical wavefront, those gaps between the two, that difference you will measure in micrometers, let's say. You multiply it with 2 pi over lambda, that gives the phase difference between the two. So 2 pi over lambda is the factor.
Thank you.
You're welcome.
I have a question about the redefined strain ratio in number 11. This a typical definition of strain ratio, but even though depends on Fresnel number, if is large or is short Fresnel number. When you conclude that the Fresnel number is inverse to the, as you put in conclusions, please, we can go to conclusions.
Just one moment. This definition is not the usual definition because in most cases the depth of focus is small. Inverse square law does not enter into the calculations in terms of changing z, because z you change only tiny bit, like 25 micrometers I said. But now I'll go to the conclusion.
Conclusions.
Which one?
Yes, you put in sentence 3, depth of focus is small for beings with large Fresnel numbers. It's inverse depth of focus from Fresnel numbered.
Yes.
So how do you measure using a strain ratio this fact?
First of all, the depth of focus is very small when the Fresnel number is very large, as I discussed the example of the photographic camera. Fresnel number was 2000, and therefore the depth of focus was very small. As soon as you are slightly out of focus, you are really big out of focus, because the change in the distance that you can tolerate is very tiny. Like I gave the example of 25 micrometers. Now, how do you measure it in the lab? As I said, I don't do the measurements in the lab. I just talk about it on paper. But you go to the lab, you have a laser beam, as an example. You have to increase its size, reduce its focal distance to whatever the depth of focus may be for the example in the lab. You will find, as you make your measurements at the focus and out of focus, that the value doesn't go down or does it go up? It will go up if the Fresnel number is large. If the Fresnel number is small, it is bound to go down, because the effect of inverse square law dependence is over a very short range. As I said, 10 centimeters or 10 centimeter plus 25 micrometer, that distance z, 1 over z square is the same number. Negligibly changes. It is only the wave aberration and therefore the phase aberration that changes, and those aberrations can only reduce the number. And you will measure it along the axis, meaning at a point or very tiny area with a detector.
Okay. In graphs.
You have a setup in the lab that you could check it out.
Okay, thank you, Professor. In graphs, as you showed that uniform intensity, could you go to the graphs, please? For example, in this case, is otra anterior. In this one, as you
This is still
as you increase,
not n equal to 0.
yes, as you increase aberration, spherical aberration, the beam is more uniform.
No. I said uniform beam, meaning the beam is uniform at the pupil.
Okay.
And
Yes, the
if
question.
it's a laser beam, it could have a Gaussian profile at the pupil. As it propagates, it can have the same Gaussian form except it is expanding or contracting. But the amplitude being uniform, I'm talking at the pupil.
Okay.
When it goes, gets focused, you get the area pattern, no longer uniform. And similarly in between.
Okay.
And in much of the discussion I had, we were making measurement only along the axis.
Thank you.
Can we have another question?
Thank you, Dr. Virenza, for your excellent talk.
Thank you.
I would like to ask you if this kind of analysis could contribute to combine with the super resolution technique in order to go deeper in the resolution scale.
What is your question? Could it impact the resolution?
Could this result impact into the super resolution field, or they are totally unmatched?
My short answer would be, for resolution, number one, you have to look at the distribution across a certain area, not just at one point. Because how do we define resolution? As Remy said, the first minimum of the area pattern falls on the principal maximum of the other if you have two-point resolution. So you have to look at the total distribution, such as, say, across the areas and so on. And that can be done. And then compare the resolution you then obtain with the usual case. But I have not done that kind of work. But certainly it can be done. Maybe some student can work on a project to do the calculations.
Okay, thank you very much. The second question is related to the properties of the beam that impact the length. What about if we have some kind of laser beam that are with the property of vortices? Like bezel beam, something like that. How the parameter of the beam of that kind would impact on your results presented today?
My own guess is the basic results will still exist, but the actual results will vary depending on the distribution of the amplitude across the beam. It was easier calculation, closed form calculation for a uniform beam, and even for the Gaussian beam, it's not a closed form solution. And therefore, you have to use computer software to get those results.
Thank you very much.
You're welcome. Anybody else?
A question. If the focus aberration has been balanced with astigmatism and spherical aberrations, the detector, if I want to measure the wavefront, in which place the detector must be collocated?
Yeah, two things. Detector is along the axis to get the results of the vary with the value of C. But the aberration is introduced to the pupil plane. In the first case, the beam is aberration free. It's a spherical wavefront. Now we introduce spherical aberration in the beam. And the amount of spherical aberration and the sign of the aberration has to be of the right kind. Because if I'm choosing the wrong sign, it won't balance the defocus aberration, it will increase the sigma. But it has to be introduced in the plane of the pupil. The observation you make along the axis.
Thank you.
Here we have another question.
Good morning, Professor Mirendra. I have a question about the Fresnel numbers. The calculus of these numbers can be applied for diffraction, Fresnel diffraction, or also for Fraunhofer diffraction.
First of all, I am hearing Fresnel. Fresnel, he was French, and the pronunciation is Fresnel. Let's keep in mind. I understand sometimes I may not say it right, the Spanish name and so on. So it's Fresnel. I'll give you an example before I answer your question. I think I mentioned it to some of my students. I was at a conference in India, and there is a young scientist, she's giving a talk on whatever. And the name Poisson comes up. You have heard of Rayleigh distribution, Poisson distribution, and so on. Poisson is another French person. And the pronunciation is Poisson. And she was saying, and Poisson said this, Poisson said that. So I come listening, finally I had to tell her, it is Poisson, and it is a French mathematician, French scientist. But anyway, your question is it Fraunhofer or Fresnel? I hope some people know what is Fresnel diffraction and what is Fraunhofer diffraction. If here is the pupil, and let me go back so I can give a decent answer. Daniel. I cannot move.
But which shot? Which shot do you want?
I want to go back maybe 10 or more, maybe 15 or more. If I have an aperture here, you shine light on it, and you observe the so-called diffraction pattern. If you observe it relatively close to the aperture, it is called Fresnel diffraction. If you go far away, and there is a way to define what is far away, you see the Fraunhofer pattern. Here, if I am making a Let me try. Go back some more. Yes, leave it there. This is the pupil, radius A, some distance R. Generally, in our problems that we work on, this distance R is much larger than this radius A. If you make observations in this region, close to the pupil, that's Fresnel diffraction. If you make observations in this region, now it is focused, that is Fraunhofer diffraction. What is the difference between the two? Those of us who know a little bit about aberrations, the difference is simply the following. Fraunhofer diffraction, we don't consider the defocused aberration. As we come closer and closer to the pupil, defocused aberration is increasing because the beam is focused at this distance. So, for us, those who understand and know how to calculate the diffraction pattern in the presence of aberration, Fresnel diffraction is simply the defocused Fraunhofer pattern. Fraunhofer pattern in the presence of defocused aberration. So when I was showing my charts, I was sometimes in the Fresnel region and sometimes in the Fraunhofer region. Only if I am very close to the pupil, then it is neither Fresnel nor Fraunhofer. So my results, whatever I showed, they are good for both, depending on whichever region you are making the observation. Any other question?
More questions? I have a question about application, Professor.
Where are you?
Here.
He is in the Fresnel zone. Fraunhofer is in the
Our applications, for example, in confocal microscopy, you need to focus and you're scanning sample. I suppose this theory is a good study for this kind of applications, confocal.
My experience with microscopes is negligible. Most of my experience is with imaging, large telescopes, and so on and so forth. I'm not sure how to answer your question or even how to understand your question. But we can discuss it. We don't have to discuss it in front of everybody.
Vamos a pasar a darle su reconocimiento al profesor. Thank you, Professor, for your conference. Thank you so much.
Now we're going to give a certificate of recognition to Professor Mahayan. It says, Universidad Politécnica de Tulancingo presents this certificate of recognition to Professor Virendra Mahayan in grateful appreciation for having shared your knowledge as a lecturer in the axial irradiance of a focus beam in the first research meeting of postgraduate students, carried out 18th, 19th, and 20th June in Tulancingo de Bravo Hidalgo. Signed, Dr. Arturo Gil Borja, Rector. Thank you. We have a small present for you too.
Very nice. Thank you very much. Thank you very much.
You're welcome.
Thank you.
Plaza, please.
I hope the weight of my suitcase won't go up.
Thanks very much. I appreciate it.
Your love,
For me, is more of a gift than any of these.
but
I will take it home and put it on display in our family room.
thank you very much.
Jóvenes, los invitamos a que continúen con nuestro ciclo de conferencias, los que van a pasar a las salas contiguas y los que se quedan en este recinto. Gracias.